Okay, so let's go ahead and I'll start with any questions you might have. This is day. No questions? Over the what do you want me to do? Number 6 on what? 7.3? The one that we were just talking about a little bit? Oh, it was. Wow, they look almost the same. Yeah. Okay, so the problem I'm being asked about is on page 385, number 6. It gives you y is equal to 4x minus x squared. It gives you y is equal to x. And the instructions are, use the method of cylindrical shells to find the volume generated by rotating the region bounded by the given curves about the y-axis. So you want this about the y-axis. So I first need to come up with a picture of what's going on here. And to do that, some understanding of what these functions look like will help. Y equals x is your diagonal. And then 4x minus x squared is a parabola that opens down. So I think what I'll do is I'll start by trying to figure out where these two functions hit each other. So I'm going to find their intersection. So set them equal to each other. And this is just a quadratic equation. I can move everything to one side, so I'll subtract x on both sides. Get this. I'll factor out a GCF of x. And that gives me two answers, 0 and 3. Is that all right? So what I know is that when I graph these, they will hit at 0 and 3. I actually know that the y equals x line looks like this. So I know that one point of intersection is here and the other one is up here. The only thing I really have left to do is resolve where that parabola is. Like, where is it relative to that green thing? Is it, it should be above because it opens down, doesn't it? So why don't we just check a couple of points. What's the value of this parabola at 0? 0, so it's here. And at 3, we know it's here, right? That's where they intersect. So let me plug in 1 real quick into this. What would happen if I plug 1 in here? I get 3, so I'm up here somewhere, right? It'll be even with the other dot, actually, but most important thing for me is that I know it's going to look something like that. It's above it, and that helps me to make sure that I know which one is the top function, which one is the bottom function. I want to rotate this around the y-axis. So my axis of rotation is here. Right, my axis of rotation. I'm using shells, which means the rectangle that I'm going to draw is going to be parallel to the axis of rotation. Washers would not work here, right? Not easily. The other method, washers. All right, so strong today. No, I'm drinking lemonade and my throat hurts. I shouldn't be drinking lemonade when my throat hurts. It's like, yeah, vodka is... I think I poured too much vodka in there. What? No, my allergies have been messing with my throat today, and man. Was there a question? Yes, what? Well, when we go to the formula to try and figure out, we know shells is going to be 2 pi integral a to b. Then we need the radius, which is the distance from our rectangle to the axis of rotation, and we need the top and bottom functions. That's the 3 things we'll need for shells. So the axis of rotation, the radius, is the distance from the axis of rotation to the rectangle, which happens to be exactly the same as x, because x is always the distance from, in this case, the y-axis to the rectangle. So the x and the radius coincide in this point. There's no adjustment that needs to be made because the axis of rotation is the y-axis. So I guess you could say if the axis of rotation is the y-axis, your radius will always be x. You could say that. All right, so 2 pi integral 0 to 3. Radius times top minus bottom, 4x minus x squared, minus bottom function, which is x, dx, dot, dot, dot. All right? Yes? Mm-hmm. Yes. I'll tell you what I'm going to grade. I'm going to grade this, because I really don't feel like following all the algebra after that. And leave it. Don't even simplify it. That's okay. Just don't leave it as top minus bottom in words, you know. Just identify all those things. A, B, just write the formula down. Just give me what formula you're supposed to use. No. At least fill in what the top is, what the bottom is, and then... Okay, any others? Yes? Yes. I'm going to force you at one point to have to use shells. I may tell you to, or I may give you a region that you can't be done easily the other way. The idea in the big picture of things, you want to use the method that's going to work. And sometimes shells works at the same time washers works also. So in that case, who cares what method you use, right? But I want you to be able to demonstrate it. So I'll either tell you or you'll look at the region and go, uh-oh, I better use shells. It's the same curve, yep. Any other questions? I think we said last time no, right? I think we said no. On the other sheet, the printout ones, no. Mm-mm. Yeah. I mean, there's really only 2 formulas, right? There's Washer's method, which is pi times integral. It's the top squared minus bottom squared, or right squared minus left squared. And then you have the Shells method, which is 2 pi integral, then radius, right? The radius, the distance from your rectangle to your axis of rotation, top minus bottom, or right minus left, depending on if you're integrating the other way. Yes? Riemann sum? No, you won't have to memorize the Riemann sum formula. Will not have to do that. There was a take-home quiz I gave you where you had to do, you won't have to memorize any formula for that. Okay, anything else over homework, cross-sections, anything like that? Because we need to cover arc length and we need to talk surface area. Okay, let's do it, yes. So arc length, last class, we were able to come up with a formula, right? Yes, I did give you a formula. That the length of an arc is the integral from A to B, the square root of 1 plus y prime squared dx. And that was valid for a curve that looked like y is a function of x here on the interval AB. So if you take that curve, stretch it out, measure it, the length of it will be this. And we verified using this formula last class that the circumference of a circle is 2 pi r, right? So now what we're going to do is we're going to get a different problem, and we're going to see that sometimes this y prime squared can lead us to some kind of messy algebra. So here's an example. Let's take something. Let's take one of these even problems here. Find the length of let's try this one. I'm afraid this one's going to get ugly, but we'll try it. I'm trying to make sure I give you one that gives you the appropriate level of algebra struggle so that it's somewhat similar to something you would see on the test. There's something very specific that I want to happen. Here we go. Okay, let's try this one. Y equals 1/6 x squared plus 4 to the 3/2. On the interval 0, 3, find the length. So we're going to take this very weird looking function. We're going to find the length of it on the interval 0, 3. Understand what we're doing? We'll take a look at it first, although that's not going to help us find the length. We want it on 0, 3. I'm going to do first. Okay, there's the curve, all right? That's what it looks like. But we only want it on 0, 3. So we're only going to be looking at it here. That piece, just one particular piece of it, measure how long it is. All right, so let's see why they gave us such an ugly function. All right, let's see if there's a reason why they did that. So within the formula, I need to know the derivative, and I need to know the derivative squared, right? So let's go ahead and find the derivative. So we're going to use chain rule here. We have to first bring the 3/2 out front. When you multiply 3/2 times 1/6, you get 1/4. So 1/4 x squared plus 4 to the 1/2 times the derivative of what's inside, which is 2x. So this is just going to result in 1/2 x squared plus 4 to the 1/2. Now, I also need to square it. So let's do that on the next line. Where's my x? I don't know what you're talking about. It's right there. Wake up, okay? Now square it. So when you square x over 2, you get x squared over 4. And when you square this thing, which is basically a square root, you just get x squared plus 4. Okay. That's what's supposed to go inside that integral, right? Underneath the square root, next to a 1. So I'm ready for the length formula now. The length will be the integral from 0 to 3. They gave us that, right? 0 to 3. Square root of 1 plus x squared over 4 times x squared plus 4 dx. Now what? Distribute? You want to distribute this through? Okay. So this is where if I were doing this problem, this is what I would do. I would actually go to the side, and I would work on just the radicand. Just go try and clean this up over here. You said distribute through, we would get, I don't like that over 4. I'm going to write 1/4 x to the 4th plus x squared. Do y'all agree with that? Just distribute this here, this here. What now? You can't do that because it's separated by addition and subtraction. Solve as in substitution. Yeah, I mean, you can do a lot of different things here. Right? I mean, you can try a lot of different things. If you look at this, look, watch. Let me put it in descending order. We're supposed to integrate this under a square root, right? We haven't really dealt with anything exactly like that before. If it was a quadratic, then we have done something like that. We would complete the square and we would maybe work with it like that. But let's see. I heard common denominator, which is, maybe you could rewrite it this way. X to the 4th plus 4x squared plus 4 over 4. Could you rewrite it that way? I'm just getting a common denominator of 4 on all of these. By writing it that way, can you see something up here? What is this? It's what? It's x squared plus 2 quantity squared. It's almost like a perfect square trinomial. We need to recognize that if you actually take this and square it, you get this. In other words, we factored the top, and you factors this way. And you've got something squared over 4. That means when you put all this under a square root, great things are going to happen. Which is why they give you a problem that looks so ugly to start, because they know that 1 plus the derivative squared is going to be something nice. So any questions on the algebra here? Getting this common denominator in here is a pretty standard trick when it comes to these arc length problems. So we have this equals integral 0 to 3 square root of x squared plus 2 squared over 4dx, which is just, on the next page, x squared over 2, or x squared plus 2 over 2, right? So here we go, next page. Integral 0 to 3, x squared plus 2 over 2 dx, which is 1/2. Bring out the 1/2. And so this is a pretty clean integral here. Dot, dot, dot. All right, so that one worked out kind of nice, I guess. Bless you. Here's something that looks sort of like it wouldn't really cause us much of a problem. I wonder how long a sine wave is. Like if you take a sine wave and you take it off the page and you stretch it out and measure how long it is, I wonder how long a sine wave is. Let's see, if y is equal to sine x, and let's just look at one period. And we look at it on the interval, what, 0 to pi? One period of sine. Find the length. That can't be too bad, can it? So I need the derivative, don't I? That's not so bad. I need the derivative squared. It's not so bad either. Right? So let's now go to the length formula. Integral 0 to 2 pi of the square root of 1 plus cosine squared x dx. Now we have a problem, right? If it was 1 minus cosine squared x, we would be in business, right? Because then it would be sine squared x, then it would be the square root of sine squared x, which would be sine x, and then that would just be great, wouldn't it? So I wonder how bad that integral is. I wonder how bad it is. Let's try and let's ask Mathematica, which is the same as asking Wolfram alpha, what the integral of the square root of 1 plus cosine x squared is. And actually I'm asking for the indefinite integral, so I'm not putting limits of integration on here, which means that I just want to see if it can handle the antiderivative. Can it just give me the antiderivative function? The hell is that? Well, I'm asking you, like, what is that, right? So, I have no friggin' idea, so we're not even gonna know. Look, there are what are called error functions, all right? Essentially what's happening here is that there's no nice closed form of a function that it can give you that would represent its antiderivative. And it turns out that happens a lot. That if you were just like close your eyes and reach into the bag of functions and pull one out and say, find its antiderivative, the probability of you being able to find its antiderivative the way we have been doing, integration by parts, all that, the probability of being able to do that is 0, actually. All right, so in the big world of functions, there's no chance that you could just integrate a random function. So what we do is we use what are called power series to approximate them, and we can approximate them as closely as we want to. And within these approximations, there become errors. We're going to do power series. That's the next chapter. And there are certain errors. We're not going to talk too much about errors, but we're going to spend most of our time just trying to understand what a power series is. But this is basically the computer giving a standard error function, elliptic error function. That's that capital E at the end. Within certain, and then there's certain standard inputs for this function. X is the variable, and then 1/2 gives some sort of measure of the error that we have. So what I'm getting at is we could sit here all day and try and integrate. We're not going to do it. All right? We're not going to be able to find a nice antiderivative. So even though it seems like a pretty harmless problem, finding the length of a period of a sine curve, it's not easy to do. Now, can it be done? Like, can you actually get an answer? Well, let me go to the definite integral now. We're going from 0 to 2 pi, right? And we're going to put this in expression. Let's see if I can just copy this expression in here. And then what I'm going to do is I'm going to multiply this times 1, 0.0, and that'll give us, that'll give us a decimal answer. Approximately 7.6404. So the computer was able to get us an answer. And it's doing it using power series. But we're just not there yet. All right, we can't do it. All right? So I guess the moral of the story is what? What's the moral of the story? These functions have to be picked very carefully if we are going to be asked to find, you know. Let's do something that seems, well, I was going to have you pick one, but let's just do one. Let's do another one that gives you that practice with the algebra. See, right now I'm just having fun with trying to help you see that things can become bad. But let me give you something that would be more applicable to your life as a student in this class. So something like this. There it is. All right, you ready? Want to find the length. Please pay attention to the algebra in this problem, all right? Derivative, 1/2 x to the third, then minus 1 over 2x cubed. So what we're doing is just power rule, right? Maybe bring that x to squared up as x to -2 and then do your power rule. Rewrite it, you get this. I won't take any more time. You should be able to get that derivative. Then square it, right? Oh man, okay, so squaring it means I'm going to take 1/2 x cubed minus 1 over 2x cubed times itself, 1/2 x cubed minus 1 over 2x cubed, and then do some sort of like expansion like this. So what will we have? One-fourth x to the 6th minus, careful here, what's 1/2 x cubed times negative 1 over 2x cubed? Just negative 1/4. The x cubed on top cancels with the x cubed on the bottom. The 1/2 multiply, so you get negative 1/4. What about the middle one? Another negative 1/4. And then the outer one, positive 1 over 4x to the 6th. Clean it up a little bit. 1/4 x to the 6th minus 1/2 plus 1 over 4x to the 6th. So that is our derivative squared, isn't it? Questions? Now, I think I've learned after enough of the last few examples that I need 1 plus that underneath the root, right? So I'm going to do that now, like scratch work. What's 1 plus y prime squared? Let's figure out what that is. So just add 1 to this, right? And it turns this negative 1/2 into a positive 1/2 when you add. So now we have this, 1/4 x to the 6th plus 1/2 plus 1 over 4x to the 6th. And I'm supposed to take the square root of that and integrate it. So I said last time, what was kind of a standard technique that we use? Common denominator. Let's try and get it all together. So every one of these denominators needs to be a 4x to the 6th. Right? You get a common denominator. So this one already has a 4. So what do I need to multiply on the top and bottom? X to the 6th, which would create what on top? X to the 12th over 4x to the 6th plus, what do I need to multiply top and bottom by here to get a 4x to the 6th? 2x to the 6th on top and bottom. 2x to the 6th on top. That'll create your 4x to the 6th on bottom. The last one, nothing, just leave it. I did these as separate terms so you could hopefully see that this is this, this is this, this is this. Now put them all together. X to the 12th plus 2x to the 6th plus 1 over 4x to the 6th. Anybody see what happens there? The top is x to the 6th plus 1 squared. X to the 6th plus 1 squared. And then the bottom, 4x to the 6th, that we can take the square root of in a minute. That'll be nice. This all right? Ready for the arc length? Let's do it. The length of this curve should be the integral from, I don't remember, where was it? 0 to 2? 1 to 2. 1 to 2, square root of x to the 6th plus 1 squared over 4x to the 6th dx. Now take the actual square root, and you just get x to the 6th plus 1 over 2x cubed dx. How would you do that? Split it into two separate little terms, right? X to the 6th over 2x cubed, 1 over 2x cubed. So I'd be looking at something like this. Integral 1 to 2, 1/2 x cubed plus 1/2 x to the negative 3 dx. So splitting it into two different pieces. I'm using negative exponents because I'm about to do the power rule for antiderivatives. So this over this, 1 over this is these two things. You could pull the half out, yes. And then from there, you just, take it the rest of the way. If I give you a problem, when I give you a problem like this on the test, when you get to this, if I say, just set it up, I don't mean putting this into the integral. You would have to take it at least all the way to a simple integration. Like at this point, it would be okay. You would have to do this part. That's the most important thing for the arc length, is for you to see that this algebra.
But not the fraction. That's plus 1 over 2 cubed.
Like, yeah, this would be, my goal would be for you to get it to like here. Yeah, that'd be okay. Although I'm not quite sure that everyone would be completely comfortable going from there to there. Okay, this makes sense? Okay? All right, let's talk about surface area then. Oh, I should give you homework, huh? Well, some practice, right? So from 7.4, this is page 391. 7, 9, 11, 13, 15. What's that? Yes. Originally, on what I had circled here was 7, 13, 17. So, but as I looked at the other ones, I said, yeah, I like those. There's 5 problems to practice for arc length, all right? Oops. All right, so let's talk about surface area. I believe it is its own section. Yes. So we're going to go back to this idea of revolving a function around an axis. Right? We did that before to find volumes. So let's imagine now we take this curve, A to B, but instead of me wanting to know what the arc length is, like taking it off the paper and stretching it out, I actually want us to rotate it around the x-axis. When we rotate that, right, if we bring all the stuff underneath it also, we get a solid, don't we? The area underneath, we rotate that area through, we get a solid. But if I just rotate the function itself, just the curve around the x-axis, I get this sheet, right? This surface. And we want to know the surface area. So imagine that thing going around the x-axis. We could get the volume, yes. Yeah, that's right. It wouldn't be hollow. So it looks something like that, right? This around the x-axis. Our x-axis is going through the center of this, right? Like that. But I could put my hand through this, right? It's hollow in there. We want to know the surface area. So how could we, do y'all understand what we're trying to find? Surface area? If I wanted to paint the outside of it, how much area is there? Right? Like if I want to paint this board, I would need to know the length and the width. And I'd be able to know the area, and then I go buy a can of paint, and hopefully it covers that much area, right? Something like that. So totally different concept than volume. Arc length, I never rotated it. I just took it off the page and I stretched it out and measured how long it was. So once you rotate it, you're creating this three-dimensional object now.
Are we about to plug the ArcLength formula into
It's going to be connected to the ArcLength, but just like before, I want us to come up with this formula, like the way we've always used integrals to help us add an infinite number of things up, right? So let's imagine taking, instead of a rectangle, right? Because that's what we did when we were doing volumes, and we said, hey, what would happen if you rotate that rectangle around, right? And it created a cylinder, and we found the volume of that cylinder. That's not what we want here, right? But I still have this idea of get out of there, of wanting to take this and rotate around and taking a small piece of it. So how about taking just this little infinitesimal, just that little infinitesimal arc and rotating it around? And what would that create? So let me draw that down here. If I rotate that little infinitesimal arc around, I create this. Well, we're gonna see exactly what it's gonna be. Yeah, it's gonna be connected. Wouldn't that be what that piece is rotated around? It'd be almost like a ribbon, like a rubber band. Wouldn't it be? Like a little rubber band? Yes? It'd be a rubber band? Okay. Now, take that rubber band and cut it and lay it open. And that would give you the area, wouldn't it? Excuse me. Killing me today. Okay, so here comes that ribbon's been laid out flat. Like this, okay? How tall is it? Isn't that, be careful, hold on. Isn't that black the width of the rubber band here? Isn't it? Do you have a question? No? What's the width of this rubber band? Dx, or it could be the length of that arc, right? That little piece? What would be more accurate? The dx or the length of the arc? The length of the arc would be more accurate. Because really, if I zoom in on this little piece, look, let me zoom in on this. Here it is. Here's my zoom. If I zoom in, now we know that the actual function comes through here and it may not follow exactly on top of that black line, right? And we know that we can do a little triangle in here. This is dx, which is from here to here. But this right here is arc length is even better as an approximation. And in fact, that's what we need. So this part right here is not dx. This is, well, what's the formula that we used? It was square root of 1 plus y prime squared. That's how tall this is. Now, how long is this rubber band? Well, yeah, we need to know the radius. So here is our axis of rotation. What's the distance from here out to the edge? Whoa, what the hell happened to that? There we go. That's the height of the function, isn't it? That's f of x. That's the radius of it. What's the length of the ribbon is not the radius, it's what? Circumference, right? When I cut this and laid it out, we're talking about the total distance around would be the circumference of that rubber band. 2 pi times the radius, but the radius is f of x. So this would be 2 pi times f of x. So what's the area of this rubber band? 2 pi f of x times this dx. We should put a little dx on the end out here. Sorry, put a little dx on the end out there. That's what we did. We showed last class that this had a dx on the end because we factored it out. Go back and look in your notes. Which means that we have a formula for the surface area. It's adding up all these rubber bands, infinitely many of them. So we come up with this. Area, I'll just say A, to be understood that this is the surface area, is going to be equal to 2 pi integral A to B of the function, right, which I could call f of x, or I could call y, right? Isn't y f of x? So y times the square root of 1 plus y prime dx. Squared dx. Yes. Y is f of x. Good? Understand? Now, there are also ways that you could rotate this around the y-axis. I promise you on a test, it'll be a surface area revolved around the x-axis only, all right? All right, let's do an example. My first instinct wants me to verify the surface area of a sphere. We've never done that before, have we? Right? We've done, a while back, we verified that the area of a circle is pi r squared. We did that when we first were doing integration, right? Areas. Verified that the area of a circle is pi r squared. Last class, oh no, then after that we did the volume of a sphere, volume of a ball. And then, what did we do? Circumference of a circle, right? We've done that with arc length. I wonder if we could use this to show that the surface area of a sphere is, what is the surface area of a sphere? Radius r. It's on your formula sheet. You're thinking volume. Now look, I'm not promising this is going to work, okay? Let's just see if we can do it. Not a volume of a solid ball. What is the surface area of a sphere according to a formula? 4 pi r squared. If you know the radius, of this sphere, of a sphere, the area of it, the surface area, is 4 pi r squared. Let's see if we can prove that that's true. So what I'm going to do, well, you tell me what I should do. Arc length. Take a piece of it, right? Take that piece. Let's look at it two-dimensionally like this. Let's take a circle. Let's take just a quarter of this circle. Take that and rotate it around the x-axis and find the surface area. Yes? Double that answer and we're done. Yes? What is the equation of that quarter of that top part of circle radius capital R? Y is equal to the square root of r squared minus x squared, right? This is the third time I think we've done that. Okay, are you hesitant? What is making you hesitant about this? What do you know you're going to have to do for this to work out? What are we going to need? We need the derivative squared plus 1 to be something we can handle, right? Let's see if the derivative squared plus 1 is something we can handle. So does everyone understand I'm going to go to the arc length formula? I mean, not the arc length formula, the surface area formula, which is going to require y, which we have right there, times the square root of 1. Man, that formula I just had. I'm going to start working on getting this part resolved and hope for the best. Like I said, no promises, all right? What is the derivative of this? Yes. So I already did some of the cancellation, but that's your derivative. Then square it. Then add 1 to it. So what would you get if you add 1 to this? You have to get a common denominator, don't you? You have to put an r squared minus x here on top and bottom. So you have r squared minus x squared. Then you had the plus x from this one, right? Plus x squared over the common, which is just what? R squared over, r squared minus x squared. Is everyone all right with that? Derivative, derivative squared, 1 plus the derivative. That needs to go underneath the square root, right? But on the outside of it is what? Square root of whatever y was. So here we go. Let me try and write it all out. The area should be equal to 2 pi integral from 0 to capital R of y, which is the square root of r squared minus x squared, times the square root of r squared over r squared minus x squared dx. That all right? And that may look like a disaster, but it's going to be great. Y'all see what happens? Just rewrite this root right here as root on top, root on bottom, because that's the same thing, right? You see what happens now? Those just cancel. They're the exact same expression. And the square root of r squared is r. So we're integrating a constant. Fantastic. You could take the constant out. The antiderivative of r with respect to x is rx. So this is 2 pi capital Rx evaluated from 0 to what? R. Plug in r, what do you get? 2 pi r squared. Plug in 0, what do you get? 0. That's the answer. That's half the answer. Right? The other half we didn't do. So double that answer, 4 pi r squared. I like that stuff. I don't know if that stuff, if you like that stuff. I enjoy that. These formulas are not just grabbed out of the air, right? That's right. We did just this arc. We were saying, okay, you have a sphere, radius r. How do you find the surface area of it? We realized that you can get half of the surface by rotating just that single arc around the x-axis, finding its surface area, and then multiplying by 2. So that just verifies a formula using this thing here. Okay, so shall we? Oh, I should point out what saved us there. What made life a lot easier was that y was out there, right? Okay, let's do this one. This will be our last example. How about we take y is equal to 1/4 x squared minus 1/2 natural log x. Let's look at the interval 1, 2. Let's find the area. That'll be implied here. Find the area if rotated about, oh wait, hold on a second. Shit. I don't know about this. I think we're going to run into a major problem, but we'll go for it, okay? I think we're going to have a major issue here. Find the area if rotated about the x-axis. So the implication here is surface area. So we need to know what the derivative is. We need to know what the derivative squared is. We need to know what 1 plus the derivative squared is. So derivative, 1/2 x minus, no way, 1/2 what? Times 1/x, which is really just 1/2. We could put the 1/2 outside and do this. I didn't do that before. I kept it in there, but I could have done that. Pull 1/2 out of each of these, so you'd be left, and then minus 1/x. Square this. You get 1/4, and then squaring this would be doing your expanding, right? Foiling out, whatever. You should get x squared minus 1, and then minus plus 1/x squared. That's what you should get when you do this times itself twice, right? Times itself. So end of the day, we have 1/4 times x squared minus 2 plus 1/x squared. Now what? You want to add 1? We could distribute the 1/4. I really am tempted to distribute the 1/4 because I know that I'm going to need to add 1 to this in a second. I think we're in big trouble, okay? I think we're in real big trouble here. Put this together. Let me see. Next thing I'm doing, I should have separated. That was y prime. This is y prime squared. This is 1 plus y prime squared now, which is just 1/4 x squared plus 1/2 plus 1/4x squared. That's going to need to be under a root, so we may as well get a common denominator now. No, I added the 1. Remember, add 1 and it adds to this negative 1/2. So get a common on the next squared up top. So it'll be x to the 4th plus 2x squared plus 1/4x squared, which is x squared plus 1 squared over 4x squared. And I'm going to be able to take the square root of that, right? Let's do that now, too. I won't even do the integral yet. Let's do the square root of 1 plus y prime squared So that's just the square root of this, which is x squared plus 1 over 2x, which is really just 1/2 x plus 1 over 2x. I'm feeling maybe this is going to work. Hold on. I'm thinking this might happen. It's not the way the problem was written, supposed to go. So they wanted it in the book. They wanted us to go around the y-axis. I told you we wouldn't do that. So seeing if we can wrap this thing around the x-axis or not. Okay, any questions up to this point? Formula time? Okay, we're going to go to this. So the area should be, area meaning surface area, should be 2 pi integral, what did I say? 1 to 2? Of y. So the original function, which was 1/4 x squared minus natural log x, half natural log x, times the square root of that, which we just determined was 1/2 x, was it minus? Plus? Plus 1 over 2x dx. We got it. We've got it. It's going to happen. Okay, I'm going to take this one all the way. So I'm going to expand this out. This is 4 terms, right? Just expand it out. What's 1/4 x squared times 1/2 x? So equals 2 pi integral 1 to 2. You said it was 1/8 what? X cubed. All right, next one, here to here. 1/8 x. Next one, negative 1/4 ln x times x. So how about x ln x? Next one, minus 1/4 ln x over x dx. That all right? The first two should almost make you laugh. They're so easy, right? To integrate. This one, we have the antiderivative of just natural log by itself. What? I heard it. What? Integration by parts. I would choose u to be this and dv to be this, or the other way around. U to be this, dv to be this. I think u to be natural log x. Let's just look at it down here. If I let u be natural log x and dv, that's not dv, dv be x dx. All right, you see what I'm doing here? Ignore the negative 1/4, just right here. What's du going to be? 1 over x dx. What's v going to be? 1/2 x squared, right? And ultraviolet minus voodoo right here is just 1/2 x, which is easy to integrate. So that would work. What formula, what? It's just natural log, though, yeah. What about this one? Okay, so all right, so 2 points. First person who can tell me what to, no calculators. How to do it? So then it would become, I want the final answer. I don't want anyone, Forget the 1/4. Oh, that's it. Good. 1/2, yes, it's done. 1/2 ln x squared. Look, yes, you had the right idea. Look, the basic u substitution. U is natural log x. What's its derivative? 1/x, which is sitting right here. So u is natural log x. The derivative is there. So what's the antiderivative of u? 1/2 u squared. What was u? Natural log x. So 1/2 natural log x squared. Okay, so you got it. All right. So it can all be done. Oh, 23 minutes. It means we need to finish up. All right. So we are done. That is, as far as topics, that's it. So let's talk about. Yeah, again, I think something like this is not gonna. I'm gonna want you to take it to the point where everything's easy. And that's relative, right? The whole point. This is the biggest thing I want to see. Is the fact that you can take a derivative, add 1, and get a common denominator, and realize that that under the square root simplifies. I want to see that algebra. All right, so here, I wasn't normally, normally I wouldn't do this, but I'm going to show you last semester's exam. Don't ask me to send you a copy, all right? Don't be like, hey, can you send that out to us? That'd be great. That'd be wonderful. You want to see it with the answers? Yeah, we'll just look at it first. All right, so this is what? I mean, what are we looking at there? This is a 6.6 improper integral. This is a type 1 improper integral where one of your limits of integration is infinity. Look at what they had to integrate. How do you integrate that? That's a u sub problem. U is x squared. Du is 2x dx. You have that almost. So when you rewrite this after u sub, it becomes e to the negative u because it's down on the bottom. You bring it up. And then you integrate that. And then you have to, well, you know what? I should probably just bring up the solutions because it's probably worth just talking about that way. Here's your u substitution. So you wind up getting a 1/2 out front here. But 1 over e to the u, you bring e to the